Okay, let's go ahead and begin. So like I mentioned last week, this is the last in-person lecture. And we're going to talk about what the stack is. That's the segment that's part of real memory that goes along with the other three segments. The only one we haven't talked about yet, right? Because we talked about the code segment where the program instructions are, and we talked about the data segment. That's where you obviously will put data, like an array of data. Before I forget, I was hoping okay, so we'll talk about what the stack is, and then we'll see how to do subroutine. Then we'll see after the stack, we'll see how to do subroutines in assembly. So the first part is what the stack is, and how you can do some basic code involving the stack. And then when we get the subroutine, you'll see like a use of the stack. Also, like I mentioned last time, I'll return the midterms today, but I'll wait till after the lecture. In addition to the lecture, also, before I hand back the midterms, I want to go over the grading criteria for the final project software and also the final project hardware. And then, at the end, after you get your midterms back, you can work on whatever assignments you need to work on. Remember, this Thursday is an open lab. Okay, so what I mean by that is you can still come here if you want, but you're not required to attend. Right, you're not required to attend the rest of the quarter. But Thursday specifically is an open lab. I won't be here, but I'll be available on Zoom. And then remember, the last 2 weeks are devoted to the final projects. And again, I won't be here. You don't have to be here, but I'm available on Zoom to assist. Okay. All right. So anyway, let's talk about the stack. So it's part of real memory. And what's the segment that's below the stack? Now, this is where it might be useful to have your computer looking at. I think it's in the lab manual that it talks about like the data segments. Also, I wasn't able to get enough of these handouts that have the alternative names of registers. I mean, most tables have it, but the tables that don't, again, if there's somebody with a computer, you can probably just get it on the computer. We're going to be looking at that handout later on also. And it's a good idea always to have the instruction manual, handy before. So, but anyway, getting back to this, what segment is below the stack segment? Which one? Data. Yeah. Yeah, there's a stack data, and then code segment is below the data segment. I didn't drive here. We talked about that earlier. Okay. Now this you should know from previous discussion and also a previous assignment. What address does the data segment start at? Like 6,000. Right, hex 6,000. So it's 4 zeros, 4 hex zeros, and then 6,000. So I'm just gonna write 6,000, but understand there's 4 hex zeros before that. I'm just not writing. But yeah, it starts at hex 6,000 for the data segment start. Okay, where does the stack segment start? What address? That one we haven't talked about before, but you can look at your information on the computer. Things in the lab, everybody find it? Yep. Again, I'm not trying the first 4 zeros, but yeah, F 0, 0, 0. And how about the last address of the stack? Yeah, all F's. Again, 4 zeros. I'm not writing 10. Okay, now I also drew the border between the stack and the data segment to the dash line. I did that on purpose, and I'll explain what that signifies, a little later on. Okay, but some basics that you have to know about the stack. The first one is only words are written to or read from the stack. Okay, now the stack, just like the data segment, just like the code segment, it's byte addressable. Okay, but we never write or read bytes or half words from the stack. We only read or write words from the stack. And the main reason for that is the stack is meant to be a simple memory construct, if you will. Okay, the stack is simpler than the data segment where typically we have arrays. Okay, and as you learned when we talked about the data segment, you could put words or bytes or half words, into the data segment. Okay, but again, the stack specifically is only for words. Okay, and that's just to keep it simple. Okay, we want it simpler than what we put in the data set, such as an array. Now, a write to the stack is called a push. So when you're writing specifically to the stack, we say we're pushing that data to the stack. It's called a push. And a read from the stack. Okay, so you know what I mean by these little dash, just repeat with them. So when you read from the stack, it's called a pop. Okay. When we're reading from the stack, we say we pop from the stack. Okay. Okay, now to access the stack, keep track we keep track of the top of the stack. And I'll explain what we mean by that. But the way that we keep track of the top of the stack is with a special register. And can you guess what register by looking at the alternative names? Stack pointer. Right, stack pointer. And what register is the stack pointer? That's also on that handout. You got a handout at your table. You can look at the handout. If not, look on your computer. So yeah, register to that. And so, remember again, we talked about how the first 5 registers in the reg file, right? Register 0 to register 4. There's special registers that have special things that we use them for. Well, this is what we use the stack for, to keep track of the top of the stack. And it keeps track of the top of the stack. And the way it keeps track of the top of the stack is by holding an address. Okay, and we're gonna see examples. And this is just like I said, some basic information before we get more of the details. Okay. So any questions up to this point? I mean, it's basically this definition that at this juncture. But any questions? Okay. Well, the stack that we have here for our Otter is called LIFO. Does anyone know what that acronym means? Did you see it in a different class? My previous section. Last in, first out. Last in, first out. You might have heard of FIFO too, right? There's a FIFO, first in, first out. But this is LIFO, okay, last in, first out. So for visualization purposes, the way we think of a stack, and this is why it's called a stack, is that the first thing you put in the stack, say is this word here that I'm representing as a block. Well, then the next word you would put on the stack, you think of it as being put on top of the previous one, right? And then the next word that's put on the stack, you think of it as being put on top of that. Okay. And then since this was the last one in, this would be the first one out, meaning this would be the first one read, if it's the last one that's written. Okay, so again, this is just sort of a visual way of thinking of the stack. And again, it's where the name comes from. Now, as I said earlier, the stack, just like the data segment, just like the code segment, is byte addressable, right? So each 32-bit row, think of like 4 bytes that each have an address. Oops. However, like we said before, again, we only read or write words to the stack. So even though it's byte addressable, we never either write or read a half word or a byte. It's always a word. Okay. And the stack is filled in this direction. Okay, you may recall when we were talking about the data segment, doing the arrays, the data segment is typically filled that way, right? Starting with address 6000. You see the stack is filled this way. Now, I'll explain later why it's like this. Okay, there's a reason for it. Okay? But for right now, the question I have here that I'd like you to think about is what word address would be the first stack, or at what word address would the first stack data be at? Okay. Like I said, we're filling the stack from this direction. Right? We're going to start at the top of this picture. And you only either read or write words. So another way to phrase this question is, what is, well, I have it here, is, what's the first word address? Can you tell me looking at this here? What is it? Well, let me ask you this. What is the address of this byte? Yes, all zeros and FFF. Right, because this is the top address, right? So what would the address of this byte be? FFFD, right? Or not even, this one would be FFFD, and then C. So what would the answer to that question be? Right, FFFC, right? Because again, we're only either reading or writing words, so only the word addresses matter. Okay. They see here the first word address would be city, and this is kept in the stack point, right? Register 2. Okay. See the stack pointer always has the address of the top of the stack. And that's what we mean by like a pointer, like it's always pointing at the top of the stack. And the pointing means it has the address of the top of the stack. Okay. So the next thing to do, if there's no questions up to this point, is to just look at some example code. Okay, this is not anything special. It doesn't really tie to anything pertinent. It's just showing the instructions to push to the stack and also pop from the stack. And also it shows what you need to do to keep the pointer, right, our stack pointer at the top of the stack, namely the stack pointer register having the address at the top of the stack. Okay. So in this first, in this code here, the first line, you've seen this instruction before. LI, what does that instruction do? Load immediate. Yeah, load immediate. It's just going to take this number and put it into register 2, which is our stack point. Okay. So this is just going to put, I'm going to put this number into the stack point, right? Register 2. And what we're doing here is we're initializing the stack point. And we're putting it, see, 1 and then 4 zeros. 1 and 4 zeros is actually here, right? See, we're putting it just outside the stack segment. And you'll see why that's so coming up. Okay, so all the load immediate is doing is just initializing our stack point, right? Because you don't know what's in there to begin with, right? You can't assume, like we talked about before, you can't assume that a register has any particular data until you write something to it, right? It could be all zeros, it could already be 1 and 4 zeros, or it could be anything else, right? We don't know. All right, the next thing is we have this add I instruction. I'm missing a comma. So what's this add I instruction going to do? Down this side. Okay, what does it do here? What does it do with this -4? Why do I have, SP, comma, -4?
Subtract this 4 from SP and then store that in the value to SP.
Yeah, it's taking the value we put in SP, so it's taking this 140, it's going to subtract 4 from it, and then put the result back in the stack pointer. Okay, so this is going to make the stack pointer contents. Going to make it what? Since we're taking this number and subtracting 4, what would you get? What's 1 0 0 0 0 minus 4 in hex? What is going to be? So you see what this add I command is doing, it's putting the stack pointer, it's putting it right here, it's putting it at this word address, right, which is the top of the stack. And then what's this SW instruction going to do?
Store
it's store word, yeah.
It's going to store the contents of T0 into that stack pointer, or the place of the stack.
Right, exactly that. See again, this 0 in front of the parentheses where we have the stack pointer register. What do we call that 0?
Offset.
Yeah, we call it an offset. It's just an immediate, right? A number, but we call it an offset. So it takes that offset, adds it to what's in the stack pointer register. So it's going to add 0 to this FFFC, which obviously is FFFC. Then it uses that as an address, and it takes the data from this register and puts it at that address. So you see, this is going to put the contents of T0 at this address of the stack. Right? And put it at the top of the stack, this address. Does that make sense? Okay. So so this puts T0 data at this address. So this is an example. This is an example of a push. Right? Because we said a push is when you write to the stack. Write and a store are the same thing. So you use a store command, a store word command, to push to the stack, to put something on the stack, right? To put data into the stack. Okay, does that make sense? All right, then the next thing we do is we're going to move the pointer. Right? We use another add I, and this is going to put Yeah, so the SP contents is gonna be what, because before this instruction, the stack pointer still has this FFFC, so now we're gonna subtract 4 from it. Right, 4 from this, so if I subtract 4 from FFFC, I get. Right. Eight. So you see that moves the stack pointer, that will move it. Right, it's gonna move it up 4. It's gonna move it to the new top of the stack.
I have a question from before. I don't know if you said
So
it,
this here, the store word,
yeah, right above it, the add I.
okay,
Why couldn't we just do load immediate, OX, and then the FFFC? Okay.
you can do it differently.
Is that just for organizational sake?
Yeah, it's well, not really a convention per se, but I guess it's typical to move the pointer first and then, do the storing after the pointer's been moved. I mean, there's ways where you can, like move the pointer further and then use like the SW and the offset to, do the writing, if you will. So, I mean, I don't want you to think this is the only way it can be done, but this is probably the most conventional, most basic way, if you will. And I chose this way just because I think for learning, it's the best way to learn it, but there's shortcuts. Like you could do what I'm doing here in how many commands, like 8 commands, you could do in half. By using some shortcuts. And that's what you're thinking about. There's a shorter way to do it. Okay, but I just chose this way because I just think it's a good way to learn it. Okay, because I think the shortcuts, at least for some people, would take away like the actual what's going on, to kind of hide the principle of the thing. Because the principle of the thing is we always have this stack pointer pointing to the top of it. And when we're putting stuff on the stack, we use the store word and stuff. But yeah, there's definitely other ways. All right, but then this next store word that would put the T1 data at right? So you see that would put T1 here. Right, and then it's just getting repetitive, right? Because then we move the stack pointer again. So now the stack pointer points at what when I subtract 4 from here? 4. At 4. Right, so that moves the stack pointer here. Now we have another store word that's going to put the contents of T2 data into that stack address. Oh, no, 4. Okay, so does that all make sense? Now, granted, there's probably other ways to do it that require less instructions, but at least does this make sense, right? Nothing else, you get to see an add I and a store word command again a couple of different times. Okay, so these are all examples of pushes, right? So to do a push, you're just doing a store word, right? You're using an add I to keep track of where the top of the stack is. Okay. Okay, now if you want to pop, okay, so that's a read from the stack. Well, a pop is a load word. And remember, it's last in, first out. So the last thing we put in was T2, so that's going to be the first thing that pops out. Okay, so you can see that I have this load word and I put a 0 offset because we're already at this address of T2, right? The word address of T2. Okay, so this instruction here is just going to take the contents from the stack, right, at this address and put it into this register T2. So this is going to put contents at, we'll say, contents at 4 and put into T2. Right, so just like we said over here, up top from the stack, it's just when you're reading from the stack, right? When you're getting data from the stack. Right, a push is writing, putting data on the stack, right? Or a pop is reading from the stack. Okay, so then the next line will just move the pointer, right? So just move it down to the word address of T1, right? So that's what this does here. And then we do another load word. So that's going to put the contents at F8 into T1. Right, and then I just move the stack pointer another 4, right, to get it back to this address. Right, and that's going to put the contents of FC into T0. So when I'm done with this instruction, my stack pointer is at this word address of T0. So the last thing I would do is just do another add another 4 to put my stack pointer back to the initial value. So here the stack pointer goes back to the initial value. Some people argue, well, why use this as the initialization address? Why not just use all F's, and instead of subtracting 4, you're subtracting 3? Well, the only reason they do it this way is then everything's 4s. That's really the only reason you do that. Okay, so that's typically your initialization address is that 1 with 4 zeros. Okay, so this is, like I said, this is kind of the basics, and like the basic way the code looks. Again, there can be shortcuts, as I pointed out. Now, like the reason behind this and the use of it will come up when we talk about subroutines. But before we get to anything to do with subroutine, a couple of things I want to mention here. And one of those things I want to mention is, can you see why we would always want the number of pushes equal the number of pops? And, you can see here, whatever order you're pushing, you're doing the opposite order when you're popping, right? We push T0, T1, T2, and then we pop T2, T1, T0. Okay, and that's always true because we're last in, first out. Okay. But can you guess what would happen if we didn't have an equal number of pops and pushes? Like if we had more pushes than pops and more pops and pushes? You think of something that might happen over here between the seconds? Like what if I was pushing more than I was popping? What eventually would happen? Yeah, it's called stack overflow, that my stack would go into where the data is. Right? And that could it could cause a problem because you could overwrite data, in your data segment that you didn't intend to. Or if you had the reverse, you could try to read information from above the stack segment, which I'm pretty sure, if I remember right, is reserved. It's unreserved. It's basically just not used, but there's stuff there. Maybe all zeros might be something else. And again, that could cause issues, right? Okay, so if you don't have an equal number of pushes and pops, that's a bad thing, right? Because you could overwrite data that you didn't intend to, or read data that you didn't intend to. Okay. Okay, the other thing I wanted to point out is, like I said earlier, the data segment is filled this way typically, right? We start at 6,000 address, like you did in your assignments, and the stack is filled this way. Can you guess why they didn't make it where the stack started at this lowest address, the F0000? Do you think of a reason why they chose to do it coming this direction instead of that? Where do these, these address ranges, like this address range for the data, this address range for the stack, the address range that we use for the code. What is that determined by? Is that determined by hardware or is that determined by like a person?
We defined it ourselves.
Right, it's defined by a person, Dr. Hummel defines those address ranges in the memory module. Now, the address range of the entire real memory, that's determined by hardware. That's determined by your FPGA that's on your basis. But how these segments are divided up, that's totally the program. So, see, if we started the stack at this address here, we would be sort of setting a hard limit when we didn't have to. See, by starting the stack here, the programmer now has flexibility where this divide line can be. It's very easy. Like you can look in the memory module and you can find it. You can find where the ranges of the segments are defined. So it's very easy to change the address range of the data in the stack. Like for example, if for some reason you needed more space in your data segment, you could just move this. You could have a smaller stack and a larger data segment, or vice versa. If you wanted your stack to be bigger than what it is compared to the data, you could also do that. And so that's the reason why data is built this way, stack is built that way. It gives flexibility to the program. Okay. All right. So any questions up to this point? Because I think that's all I want to say about the stack. Well, when we get to these subroutine examples I have, at least the last one, the stack is going to come up again because you're going to see that when you're dealing with subroutines, especially when a subroutine is calling another subroutine, you can run into a problem that the stack can solve for you.
That might answer my question. I was just wondering, what is stack used for that data is for?
Yeah, that's a great question. Yeah, the thing to always remember is that the reason why the stack is constructed this way, where again, you can only read or write words, and we have this stack pointer, right, that always points to the top of the stack. The reason for that is just to make it simple, right? I mean, if you compare like how the stack works compared to like an array in the data segment, the stack is much simpler, right? Because again, data, you can put in words, bytes, half words, and therefore it's harder to keep track of the address. In fact, I don't know if you remember, but remember we did examples and I had like different things where, we put a byte at this address, we put a word, and we had to think about like, okay, what address do you use if you want to read from it or write to it, right? See, there's none of that with the stack, right? Because you don't even really have to think about it. You just have to look at where the stack pointer is because that's where you're going to either read or write from. And it's always a word. So, the stack is intentionally made simple. Okay, that's its whole, one of the reasons for having it. Okay, but then a use of it is going to come up, like a specific use. Okay, so any other questions up to this point? All right, well, let's talk about some basics of subroutines. Okay, first of all, subroutines are used for functions or any type of code that you're going to do over and over again. It's used for repetitious type things. Repetition. I always have trouble with that. Who's a good speller? Is that repetition? Wow, for some reason, I always think there shouldn't be an E there. I don't know why, but it just looks funny, but. Maybe because repeat is EA, and get rid of the A, I guess that's why. It messes me up. But anyway, if you have, repetition in your program. If you didn't use a subroutine well. You would have to take that. Code, few lines or a block of lines, whatever it is, and you just have to like keep copying and pasting it, right? In your RARs, right? The simulator. Okay, but with subroutine, it makes it easier to do tasks that are repetitive. So, things like multiplication, like you'll see subroutines that can do multiplication or division or sorting or delay. And in fact, for your final project software, that might be a place where writing a subroutine that does a delay might come in handy. And we'll talk more about that when we talk about the final projects after the lecture. So anyway, and you can probably think of some more things that you might use a subroutine for. Now, the advantages of using a subroutine is that first, you achieve what's called modularization. Actually, I got to look to see how it's spelled. It's easier to explain what it means than to actually write it. Oh, it's in my other notes. Done like this. Yeah, spelling was never my forte. And I'd have trouble spelling forte, so. Actually, I know how to spell forte. There's an E, not an A on the end. Yeah, so modularization. Oh, actually, I think I had it right. It's module. It modularizes your code. And what we mean by that is that, it's a way of taking a big problem and splitting it into smaller problems. Right, that's like a key aspect of engineering, right? It applies not only to coding, but anytime you're doing solving any sort of problem, right? If you got some big complex sort of problem, right, it's easier to take that big problem and separate it into smaller problems and then solve the smaller problems, and collectively that leads to a solution to the bigger problem. Okay, so that's one of the things subroutines are suited to do. Another reason to do a subroutine is it makes your code more readable. Readability. Is there an A or either? And I think that goes without saying, right? Again, you've got like a big program, and now you're splitting it up into smaller. Essentially, the subroutines split it up into smaller programs. Well, it's easier to see what the overall program is doing, so it's more readable. Also, it makes it more reusable. Reusable. Is there an E there? No E. Thanks, so much. Cool. But it makes it more reusable, and this gets into how our registers are used, how our looking at your sheet there, your handout, how we have some registers that we say are argument registers, then we have other registers that are for temporary, then we have other registers that we call saved. Well, by using those registers for specific needs, it makes it more reusable. Okay, so this gets into the registers that we have labeled A registers, and like the temporaries, the T registers, and the save registers, the S registers. And I'll talk more about that coming up. But again, subroutines are good for when you have a lot of repetition. They make your code more modularized, readable, and by using these registers that we're going to get to in specific ways, it makes it more, reusable way. makes it more mobile, where if you have a program and you follow this protocol that we'll talk about, well, you can take it to someone else and it should work with their program. Okay, so writing a subroutine. Parameters are the values given to the subroutine. So for example, if you had a subroutine that was doing multiplication, the two numbers that you're multiplying, those would be the parameters, right? Because parameters you pass on to the subroutine and then the subroutine operates on it. Now, the key thing to remember here is that when we say like the subroutine is, giving values or passing values, really what we're talking about is that those values are being put in registers, right? Because, what should be apparent by this time in the class is that in order to operate on any sort of value with your otter, it has to be put in a register, right? Because in order for the ALU to, do whatever it's going to do, add, subtract, or whatever it is, that data, those values, they have to be in registers, right? Because the otter operates on registers. And then the return value, that's just the result. All right, so again, the multiplication example, you multiply the two numbers together, which are the parameters. The answer, well, that's our return value. That's the result. Okay, so now we get into like the protocol and why, when you look on that handout, some registers are called argumentative or argument registers, right? The ones that begin with an A. The ones that begin with a T are temporaries, and the ones that start with an S are saved, right? The alternative names. Okay. Well, registers A0 through A7, those are the argument registers. Those are for parameters. Okay, and you can look on the sheet to see specifically what registers, A0 goes with and A1 and so on. Now, A0 and A1 of these argument registers, those are specifically for the return value, so the results. Return value. Probably in most cases, a subroutine is just returning one answer, like the multiplication example, right? You're multiplying two numbers, so there'll be one answer. And if you have one answer, you're just going to use A0 for that answer. But you could have a case like a divide by module where you're interested in not only, the end result. Now I can't remember if that's, well, I think it's the quotient, right? The end result of the division. And you might want the remainder too, So in that case, if you wanted two results, you would use A0 and A1 for those two results or two return values. Okay, then ideally, the temporary registers, which are T0 through T6, the subroutine ideally would only affect these temporaries. Okay, so ideally, keyword being ideally, we'll talk about what you can do if you have a non-ideal situation. But ideally, the subroutine only possibly changes these registers. The temporaries. And ideally, a subroutine does not change the saved registers. Okay? And did I get this right? I did this from memory, S11. Is S11 the highest? Is it? Okay. That was 11. So there's 12 save registers, there's 7 temporaries, there's 8 argument registers. And again, these two are for return values. Okay, the last thing, and we'll take a short break, because I want to take a short break before we get to this code for some reason. But the last thing I wanted to show you was how, when you have a subroutine, how it affects a flowchart. Because you've done a number of flowcharts now in your software assignments, so you should have a pretty good idea of the different symbols that we've been using. But we haven't done a subroutine yet. So you might not have seen this symbol before. Okay, see this rectangle with the two bars on the end? That's the flowchart symbol for a subroutine. And you would put the subroutine name right in the middle here. Also, what's different is when you have a subroutine, instead of starting it with, this oval with start like you've been doing, you would actually write the name of the main program, or you could just have it as main. But it could also be something descriptive, like if you had a descriptive name for your main. Okay, so that's what's different, along with you would add the subroutine symbol whenever the main gets to that point where it's going to run the subroutine. And then you have another separate flow chart for the subroutine. Okay, and you start it with the subroutine name. And then instead of ending it with N, you end it with return. And you'll see why this is called return when we get to the code part. Okay, so again, just an example of how you would do a flow chart when you have a subroutine. So before we take a short little break, do you have any questions up to this point? No questions? Everybody's good? Okay, so let's take a 5-minute break just till like 1 or 2 past 1, and then we'll talk about the 2 different pieces of code I got up there for subroutine, and I'll go over the grading criteria for the final project, and then I'll return your returns. Okay, so let's go ahead and start up again here. So I've got a couple of, and I remembered to turn the camera. Actually, it was a good time to take a break. So I turned the camera. But I have an example of just kind of a standard, main program calling a subroutine. And then I have an example where the main program calls a subroutine, and then that subroutine calls another subroutine. Okay. So first, let's start with this one here. Now, I put this assembler directive.txt just so I could remind you that, that's something we did talk about earlier. But, remember, if all you have is code, like you don't have like a data segment above this, you wouldn't need that .text, right? Because it's going to default to .text if you don't have it. But I put it there just as a reminder kind of thing. Okay, so, and this is, as you can see, very generic. Okay, that you got your main program, there's some instructions, and then, within the instructions of the main program, you want to use a subroutine. Well, in assembly, the way you go to use a subroutine is by using a call instruction. Okay, so it's call and then a label. Okay, and you can see I put the label for the sub down here, and this is where the subroutine code would be. Now, I intentionally didn't put something here, right, that we would want. What would we want between the last instruction of the main and where the subroutine begins? Well, not necessarily the end, but we want it to automatically go to search. Right, so that's where we would remember, because we saw this earlier that, like you have your assembly language, and you get to a point where, you don't want this code to go into the next code, right? Because it's not what you intended to do. So you put what we call a trap, right? Where you just put like another label, like we can use done, and then you just put a jump going to that same line, right? So once it gets here, it just stays. That's called a trap. Okay, right? Because once we're done with the main, we don't want it to go into our subroutine. Right? We only want to go to the subroutine when we call it. Now, this call instruction, it's a pseudo instruction for a JAL command, the JAL instruction, right? And we talked about this. In fact, we did the data path and the control signal for JAL. And the key thing here is the L. Like, what does the L stand for? stands for link. And then what's meant by a link? In fact, when we did the data path, and this is the reason why I put the diagrams on each of the tables. Like if you were to look back at the data path in control signals for the JAL command, see this connection on the left side of the +4, so where the program count, right, the address of the next instruction has been incremented by 4. It goes up to one of the inputs of the MUX above the reg file where the write data is. And if you were to look at that data path, you would see that we write the PC+4 address to a register in the reg file. Right? That's what the link means. See this link, we're taking PC+4, which is this instruction right here, right? It's the instruction right after the call. And we're putting that in. We're putting the PC+4 into register RA. And what does RA stand for? Return address. Because, see, we want to save the address of this instruction after the call, because that's where we want to return once the subroutine is done. Okay? Does that make sense? And what register is return address? Like you look on the handout there, what register is the return address register? Like the SP was register 2. Yeah, this is register 1. Right, so you see now you've seen the specific use of 3 of the 5 special registers, right? Because we talked about X0. What's X0?
0.
Yeah, the 0 register, because why?
It's always.
Right, we make it always 0. And then X1 is your return address register. It's going to hold the return address so you know where to go back to when you're done with the subject. And then the SP, the stack pointer, well, that's to see where the top of the stack is. Now there's 2 other special registers. There's a global pointer, and I think that Fred something or other, I don't remember the name. Those we don't use in this much. You don't have to worry about those. Okay. All right, so that's what's happening with this L, this link. It means it's saving this address to the return address register. Okay. And once it hits this call, it's going to go to the subroutine, and it's going to run the instructions that are in the subroutine. And then it hits this return at the end of the subroutine. And that's when it's going to go back to the address that was saved in the return address register, right? So the PC+4. So it's going to go back to the instruction after the call. And the return is also another pseudo instruction. It's a pseudo JALR. Okay, so again, it has an L in it, which means a link. So this is also going to save the instruction after the return. But notice that we're using register 0 to save that link. And why is that?
So you don't want to list a register that could be used for something else.
Right, and more importantly, I mean, that's a good answer, but more importantly, that other register could have data that we want to keep. And you see, this data would overwrite whatever register you put here. But by putting X0, are we going to overwrite anything? No, because X0 is always made to be 0. And, you know, we're never going to get to an instruction after this return anyway. Right, so this PC+4, you know, this link address for return, it's not important because there's nothing here anyway. But because of the link, it's got to be saved somewhere. And we save it to X0 because that way we don't overwrite a register that, you know, we might need the contents of. Okay. So, you know, the main points here, I guess, is just that, you know, a call instruction, it's a pseudo of a JAL. It's important to understand what that L means, right? Again, it's a link. You want to save the address of the instruction after the call, because when you return from the subroutine, that's where you need to go. Right? So you got to save it somewhere, right? The otter has to save it somewhere. So it has it here when we get to the return. that make sense? All right, is that good? Because now we're gonna talk about when a subroutine calls another subroutine. And here a problem arises that we can solve with the stack. Okay? Are you ready for this? Okay. Again, you don't need the text there unless you got data from it or something. But you can see, here's our main program. We got a call to this subroutine 1. So just like we talked about here, anytime you have a call, it's gonna say PC+4 to the return address register. So you see, it's gonna save this address, right? The address of the instruction right after the call. So that's where we want to return to. Right? We're done with sub 1. Okay, now we're in sub 1, right? Subroutine 1, we're doing some instructions. We hit another call, right? But this call is calling a different subroutine. Well, the same type of thing's gonna happen here, right? That it's gonna take PC+4, it's gonna take this address after the call to subroutine 2 and put it in RA. Okay, good. Nothing new, right? Okay, so now the call takes us to subroutine 2. It does these instructions and it hits this return. So where's it gonna go when it hits this return? What's in RA right now?
Instruction after sub.
The address of the instruction after sub 2. So this return will go right here, right? But now we do these instructions and we hit this return. Do you see the problem? Because where's it gonna go? Is it gonna go back to main? No, why not?
Go back to RA.
Yeah, because we wrote over this address here with this call.
Right.
So you see, when you hit this return, it's just gonna go back to that instruction after the call to sub 2. And it'll just get stuck there. All right, so does everybody see the problem? I'm gonna show you the solution in a moment, but before I show you the solution, do you see the problem? Okay. Well, a solution is to use the stack. Because what we can do, and I always forget a different color when I get to this point, you get a different color. Green for solution. Green money, and money's always a solution. But you see, what we can do to solve this problem is right at the start of this subroutine 1 right here, we can push RA to the stack. Right, so essentially, we're taking this address and saving it on the stack so we don't overwrite it here. Or well, RA will still get overwritten, but we won't lose that address because we put it on the stack for safekeeping. Okay, so then, let's see, and then you'd have to have a puck, because remember, every push has to be equated with a puck. You know, before we get to this return, we would pop it off. Does that make sense? Right, and we're maintaining, you know, we're not losing this return address. So when we get to this return here, instead of going back here, we'll have this in, right? Because we popped it right here, so we put it back into RA. And that will take us back to me. So, you know, that's an example of a use of a stack, is that if you run into a case where, like in the execution of your program, if you're overwriting some register that you're going to need later, well, you can put the contents of that register on the stack for safekeeping, right? So you have it for later. We're essentially, you know, putting it back into the return address register later. Now, another use of the stack is, and this is why I put, you know, ideally only the subroutine affecting temporaries. I mean, sometimes you can run into a situation, you know, if you have a large program, you got a lot of data that you're working with, you can run out of temporaries. You know, there's only how many? There's only 7 temporaries. So you can use the stack essentially to, kind of artificially increase the number of temporaries you have, right? Because you could put some temporary content onto the stack for, for a time, and then, use those registers for, things that are changing. So a stack is another way that you can possibly extend, artificially sort of, how many temporaries you have. Let's see, is there anything else that I wanted to talk about? I think those were the main things with subroutines. Now, we're going to talk about the grading criteria for the final project, both the hardware and the software. And you'll see that part of the final project software is writing a subroutine. I've modified one of the software assignments that we skipped over, and so that you have a chance to write a subroutine. I don't think I mentioned earlier, but if you've had experience with functions, like in other languages, like say Arduino, a function in Arduino is the same thing as a subroutine in assembly. Yeah, you might have known that even before today's class, but in case you hadn't heard, they're the same thing. Okay, well, let me show you what the grading criteria for the final project are. Do that, we're going to look on Canvas. So does anyone know, is this supposed to rain later today? Does anybody know if it's supposed to? I'm just wondering if I have to walk back to my car tonight in the rain. You got an hourly forecast?
It's supposed to rain.
But it'll be 0 inches for it.
0 inches of precipitation. Oh, so it's not going to be a lot of rain. Okay. Yeah, because I like park down Grand. Because I refuse to pay parking at a place I work at. No, seriously. Every place I've ever worked at, I never had to pay where I park. And I paid here when I was a student. I was like, I'm not paying when I work in here, so I'll walk. It gives me exercise. So if you ever see me walking down Grand, that's what I'm doing. Walking to my tent. What happened to it? Oh, wait a minute. So. See, I know an easy way to solve the parking problem. You know how they charge a ridiculous amount of money for you to park here? You know how you solve it? If we could get everybody, like all students, all faculty, just to park anywhere in San Luis and like walk to campus, you see the next day they would get away with the parking or do away with the parking fees, right? Because they couldn't tow enough cars, right? There's a lot of rebels. Okay. That and parking tickets really gets. You ever see that show Parking Wars? You ever see it? It's like on one of the I don't know if it's like Discovery or History or something, but well, hopefully nobody has like a relative that's like a parking meter person. But I've always thought there's a special kind of person that has to take that job, right? Because they get gleeful when someone's like just getting back to their car, like a minute late and get like a $30 ticket. I don't know. I don't think I could ever do that. But anyway, let's get back to this. Sorry to get off track. All right, so this is the software final project. So what I did is I took software assignment number 4, which is one of the ones we skipped, and I modified it a little bit where you have to write a subroutine. Now, first thing that's down at the bottom here, I'm assuming that the same teams that have been doing the software assignments throughout the quarter are gonna be the same teams that do this assignment. Okay, so if I don't hear from anyone, I'm assuming the same team. Okay, so if you want to change teams for this, like you want to partner with somebody else, you need to tell me before like the end of this week. Okay, so there's 2 people working on this. And you can see, I want you to write an assembly language program that chooses between 2 subroutines based on a value at this address of real memory. If the value is 1, part 1 of software number 4 is run. If the value is some other number than 1, then part 2 of software number 4 is run. Okay, so essentially each of the parts is going to be a subroutine. And the main is just, from a value selecting which one to call. Now, as far as what you submit for grading, it's the same criteria as the software assignments, right? The same 3 criteria of which one is a flow chart. Now, as we talked about earlier, what's different with the flow charts is that you're going to need, instead of just 1 flow chart, like the software assignments you've done, you're going to need 3, right? You'll need a main flow chart and you'll need 2 separate subroutine flow charts. And then each partner has to take responsibility for one of the subroutines. So, in the comments, preferably at the top, have the student's name who's responsible for that subroutine. Okay, so I think I talked about everything that's up here. Also, in addition, now, these additional requirements may not apply to both parts. Okay, but for the parts that it does apply to, you do want to show a result of 0. And also, if there's a division by 0, you want to show an error message in some fashion. Like I said, it's up to you how to show the error, but when you're doing anything with the divide by 0, you want to somehow display that that's an error. Okay, so is it clear what I'm asking here and what the requirements are and how it's going to be graded?
Is this just a software part of the final?
Right, yeah. Yeah, there's 2 parts to the final. Well, let's back up. There's one more hardware assignment, right? Hardware 6, that's due this Friday, March 3rd. That's, getting your auditor to run that sample program with 6 instructors. Then there's a final project software, which this is, and this is due Friday, March 10th. And then there's the final project hardware that I'm going to talk about next. That's due March 17th, which is the last day of the quarter before finals week. Okay. All right. So before I go to the hardware final project, what that grading criteria is. Are there any questions on this one? Is this clear what to do? Good. Okay. So let's go to the hardware. Okay, so for the final project hardware, this is where you can have a group up to 4 people. Right, because this is the one where you got to get your auditor to work for all instructions. Okay, so there's going to be some troubleshooting to do. And unless I hear from you, I'm going to assume that you're just staying in a 2-person group because, it's up to 4 people. So if you don't want to have 4 people, if you want to just stay with 2, that's fine. If you want to have a 3-person group, that's fine. But, no 5 people or more than 5. I mean, if a person wants to do it by themselves, that's okay too. Although, like I said, I don't recommend that. Okay, so again, if you're in a 2-person group right now and you're going to go to like a 3 or a 4, tell me. Okay, preferably by the end of this week. I've only heard from 2 groups so far. I've heard from one group in my 3 to 6 and one group in my 8 to 11. I don't think I've heard from anyone in this section yet. Okay, but it's still kind of early, but the earlier you tell me, the better. You just send me an email and just say, Gary, these are the people in my group, our group, whatever. Okay, so what you need to do for the final project hardware is you make a video. Okay, and there's 3 things to put in that video. Okay, one thing to put in that video is to show me that your auditor runs the all test mem file successfully in Vivado, right? A simulation. And I show you exactly what I mean by that in my video. Okay, in that video I made, I show you exactly how to make sure that it's working in Vivado, the simulator. Okay, that's one thing to put in the video. Another thing to put in the video is to show me that on your basis board, it's running that all test mem file. And again, in my video, I show you what it should look like. Okay, because this first part right? When you show me it's doing what it's supposed to do in the simulator, that tells me that your CPU is working the way it should, that's running all the instructions. And then when you show me that it's working on the board, that tells me that you connected up the auto wrapper correctly. Okay, and also your constraints file is good. Okay. Okay, and then the third thing to show me in the video is that you can program the auto to do something. Now, like I said last week, you can just take one of the software assignments you've already done, or you can take one of the examples I did in class and just make a men file of it and program the otter and then show that it's doing that program. Now, this is where you're likely going to have to modify what you already have, because you're likely going to have to put in delays, because if you've got, you know, one of your assignments or one of my examples where the switches are being used, you're probably going to have to put a delay so that gives the user time to change the switches. You might also need a delay on the output side, right? If you're outputting, you know, different data successfully, you know, you'll have to have a lapse of time so you can see the change in the output, like your 7-segment chain. Okay, so you probably have to put a few second delay. You know, like I think when I did mine, I had a delay on the input side. I didn't need a delay on the output side, and I put like a 10-second delay to give me time to change the switches, because you know there's 16 switches and I'm old, so you know I need time. You might not need as much time as I do, but you got to have some sort of delay there, right? I did an example in class that showed you how to do a delay, right? It's just a loop, right? You got to figure out, right, by how much time each instruction is, you know, how to get a certain delay. So, and you know, that's something that you might want to make a subroutine out of, although you're not required to. There's no requirement of a subroutine in this part. So, just to be clear, it's just one video that you're submitting. It's just in that video, you've got to show these different things. Okay. Try to keep the length of the video between 3 and 5 minutes. I mean, if you're a little above 5 minutes, that's not a problem. But if it gets to be like, you know, 8-10 minutes, that's too long. Try to shorten it. All group members have to be seen in the video at least for a split second. Okay, so that's the video. And then material to be submitted. I want a hard copy of your assembly language program fully commented. And also make sure in the comments near the top somewhere to have team member names. So I know, again, who's in the group. Submit a zip file of your Verilog or system Verilog, depending on, you know, whether you use Verilog or system Verilog, that's also fully commented. Now, this is very important because you won't get credit if this is omitted. Each of these files, they have to have a date creation, you know, like a day and a time creation along with the person's name. It doesn't have to be everybody's name in the group. It could be just the person that was responsible for that file, but it's got to show the date and the time that that file was created. If that information's not there, you're not going to get credit. Okay, and then there's also a peer evaluation, and I'll show you that form coming up. Okay, so before I get to the grade criteria, any question on what to submit, right? The video along with.
Does I feel like when it's one person or a certain person has to make a certain number of files, and the other person has to make a certain number of files.
No, it's just one submission per group, and yeah, it's okay, because what I'm thinking will happen in some cases is probably, you know, at least what I'm hoping anyway, is, you know, each person again is kind of doing their own thing, or you've been doing your own thing for the most part, right? Because all the different individuals you've been doing every week. But, you know, maybe this person's reg file works and this person's doesn't. Yeah, so that you would use that person's, you know, and, yeah. So I would expect hopefully to see like a mixture, but it doesn't have to be. It just has to be, you know, people in the group. You know, no like names from outside the class, you know, obviously, right? So, yeah. Any other questions before I get to the grade criteria? Okay, so the grade criteria is this. Okay, if you have a working auditor that runs a program, so you have an auditor that passes the all test on the simulator of Avado, it passes the all test on the board and it runs your program successfully, that can earn up to an A. Now, the reason why I have up to an A is because it could be something less if you have a less than stellar peer evaluation, or if material that you submitted, like your files weren't commented or something was missing, then it could subtract from that. But provided you provided everything and your code is commented and you get a good peer evaluation, well, that would earn an A. Okay, so that's what I mean by up to an A. Now, if you have an otter that it passes the sim test, right? All test works in the sim. It passes the all test on your board, but for some reason it won't run a program. Okay, like you weren't able to program it, or you were able to program it, but it doesn't work exactly the way you intended. That can earn up to a B. And again, the reason I say up to is because there could be things missing. Also, to earn up to a B, you would have to show a chronological list of what you did to troubleshoot, like what you did to troubleshoot to try to get the program to work. Okay. All right. If you have the next situation where your otter works in the simulation, but it won't work on the board for some reason, and if it won't work on the board, you won't be able to program it. Well, that can earn up to a C. Okay, again, you have to provide a chronological list of the troubleshooting you did. Okay, then the next tier is, it's not working in the sim, it's not working on the board, so clearly, again, you can't program it. But as long as you tell me how you troubleshot it, again, chronological list, that can earn up to a D. And then the last tier is, again, it doesn't work on the board. Well, it doesn't work in the sim, doesn't work on the board, therefore it can't program, and you don't provide me a list of what you troubleshot, then that's a failing grade. Okay, so any questions on like these different tiers and what I mean by up to? I would think someone here wouldn't get less than a B. Like they didn't get an A and they didn't provide everything, I would still think you deserve a B grade at least, right? Because you got the whole thing to work and you were able to program. And like here, probably the lowest would be a C, But I'm counting on that people submit what they need to submit, and that way you can get the highest score for that tier. All right, so any questions about how it's graded? Is that pretty clear? Okay, last thing before I turn back your midterms is peer evaluation. Okay, this is on Canvas. This is what it looks like. Get better. It's more. Okay, because one person can have 3 team members, there's 3, maximum of 3 people that you can write. So just for each person, you would just fill out either exceptional, above average, average, below average, or you can also put a comment. Comment's not required, but it's there if you want to make a comment. And as I have here, please provide an honest, objective evaluation. So what I mean by that is, whether you like the person or not should not come into play, right? It should just solely be on, whether they, contributed the way they should have contributed, easy to work with, that kind of thing. This is very typical in industry. Even here at Cal Poly, we have peer evaluations. Like every 3 years, I'll have a colleague come in, they watch me teach, and they make suggestions and constructive criticism, all that. And it's very common in industry. So my feeling is you might as well get used to it now. Okay, so let's see what else. I think that's all before I turn back your midterms, unless there's more questions. Any more questions? So everything's clear. The other thing, like I mentioned last week, you are being evaluated on troubleshooting. So, while I'm available to help, my help is guidance. It's not looking at your code and saying, oh, well, you got a 2 here instead of a 3 or something like that. Okay. My my guidance is things like, well, if you're having difficulty, I'll ask, well, have you tried this? Have you looked at this? Okay, you're getting this, but have you looked at this module? You're getting this at the output, but have you looked at the input of this? Things like that. I'm not gonna like sit at your code and say, oh yeah, there's a syntax error here or something else. Okay. All right, so let me turn this on. I know you're dying to get your midterms, but we can hand them back to you. Okay, so just let me just explain what you're gonna see on the midterm. So when you get it back, if you see a green circle, that means that was correct, and it's a +1. If you see an NR stands for no response, so that was, you left it blank, and of course, like we said, that's, either plus or minus, right, it's 0. If you had an incorrect multiple choice, I put like an X with an I for incorrect. And then remember, incorrect multiple choice was -0.5, and then an incorrect true or false was -1. Question number 16, I threw out. Okay, because most people missed it, and after I looked at it, I felt it wasn't a good question. It wasn't really evaluating what I intended to. So I threw out number 16. Now you'll also see, let's see, it's going to be on the left side of the first page of the exam. You'll see a black box with a number. That's how many points, right? So that's, after I did this, I tallied it all up and I put that there. And then you'll see by your name, you'll see a green circle with a number. And that number is out of 10. Okay, and the way I came up with that is I took the average number of points and I just said that's a 7.5. Right? That's a 7.5 out of 10. And then, your score is based on that. So if you did above, that average number of points you got above the 7.5. If it was below, it's below the 7.5. There was a couple people that, when I figured out this number out of 10, it was greater than, so I just put 10 plus. So what I put in my spreadsheet is this number. Okay, so if you got a 10 plus, I still put a 10 in my spreadsheet, but I make a note that essentially you got like an 8 plus, right? You were more than 10. Okay. The other thing that I didn't think about, a couple other things that I did right up here. One is if you have any question about anything on the exam, so like you look at it, if you think I made a mistake or you got a question about a question or anything, send me an email. Okay, and I will look at it. I make scanned copies before I hand exams back. And once I hand the exams back, I only look at the scanned copy. I don't look at what I handed back. Okay, so if you come up to me and say, oh, Gary, can you look at this or anything, I'm just going to say, send it in an email, okay, and I'll look at it. Okay, because, whatever you told me verbally, I'm not going to remember anyway. So by writing it down, I know exactly what you want me to look at. And like I said, I will do that. The other thing, last thing, I know you're dying. I'll get back to you. But last thing, if you didn't do well on this midterm, don't panic. I know there's always a tendency for people to panic if they don't do well on tests. First thing is, this quarter, I only made the midterm worth 10%. Usually my midterms are worth more than that, but I felt because of all the other work we had to do in this class, I didn't want to make a really high percentage test. So that's why I kept it at 10%. The other thing is, remember, the quarter's not over. You still have a final exam, which is 10%. You have 2 projects, right? The hardware project, the software project. I think they're both worth 12%. So, about a third of the grade hasn't been determined yet. Okay, so there's plenty of opportunity to mitigate, if you got a low score. All right, so let me give you back to you. And then for the rest of the class, you can either work on assignments here or you want to go somewhere else. Pretty much know everybody, so I think it's something you guys not here.
Oh, I need this.
There's this one. There's this one error that kept coming out. I don't know how it reads it now, but it was so annoying. Makes it more fun. Oh, that's cases. We had changed out one of the. Yeah. I think there's something else like this. Okay, sure. If something ever. Oh, yeah. Yeah. I didn't know that. I always call 133. Now that I didn't know that. That was TV. So I just sat there and waited for my. Yeah. After the first. In sequel 33. That's like so interesting. So it's going to be granted. That day. Anytime it's anything that. Yeah, I don't understand why they didn't go. That was one thing that we about. I wanted to know if it was.
Okay. So for cases where we're using parameters, what does that mean?
Well, it's just that what we mean by parameter, those are the values that are given. Like what it's in the way values are given. Just, so for example, yeah, so for example, let's say like you want to be. Well, the two values you would just in like A1, A7, like any of them. And then the value comes out.
So just in the subgroups you can use it. So it's like I found like we had arguments.
Yeah. Yeah, it's just that G registers we have set aside here for the specific purpose. That might be
Yeah, those first items. Yeah.
yeah, like
Oh, did Derek say that?
yeah, because
I didn't realize that box was probably not a good. Right. I don't know.
Well, you know what, I'll even right now, they. Really.
Well, I mean, like. And then, but they went to they started. So I've been like. Wait, after 6, I'm like, you know, you say something, and then like, I don't know, like, I understand. It's like really bad. And so I never just don't think it's nice.
I'm not sure in the ground, but that's really helping me with my.
Are you looking forward to the? Oh, that's here.
Take pictures of the.
I got my.
Oh, yeah.
I probably had to say that. I really sure with my. Yeah, no, it's something like it's awesome. I got my first. That is. I don't know. I find it. That's actually honestly. It's not bad. It's interesting, I think it's like. Signals being sent from. But it's. It's a lot more like. We're in. The wire is.
Yeah.
So we just casually like slid our head over. Okay. Right.
On the.
Not only
was he.
So, yeah.